Hello everyone. Today I will talk about some quantum education work that's been being done with the calculus. I didn't make slides for these, but there was also mention of this work that I'm talking about today in the U.S. Computer Science Teachers Association standards, proposed standards discussion that was earlier this year. Um, So there's other people also looking into this, but I think so far the experimental work has been done by this team here. So this is a collaboration between the University of Oxford Computer Science Department, as well as involvement from the Physics Department and the Mathematical Institute, as well as Quantinuum and IBM Quantum. There's quite a few names on this. So this is just pictures of the people involved, as well as this doesn't include all the tutors. So it takes a lot of people to teach a lot of students. These are high school students that we're teaching. But I'll first show kind of what is quantum pictorialism, at least the way that the approach to teaching high school students quantum information science concepts. So here is here are some notes from a master's student's notes on quantum teleportation in a graduate course. This is a course at the University of Waterloo. Actually, these are Sarah's notes. So, so oftentimes it's quantum teleportation is like taught as here's the circuit, and if you wanted to check that indeed on an input state, it gives the correct outcome. When you do the right corrections, you can try all four possible measurement outcomes, and you can kind of do a lot of bracketization to calculate at the end. And I will say that this is really challenging to teach at the high school level. So even if the circuit is really simple, at the high school level, most high schoolers, so I think 90% of high schoolers in England or Scotland don't learn matrices, or at least they're not really tested on them. Just because it's in England, it's called further maths, and Scotland has their own separate testing. And then, and even if they do learn matrices or vectors, they do not learn this bracket notation, and they also don't learn tensor product. And tensor product is specifically something not even taught in some college level linear algebra courses. But if you want to do anything with 2 or more qubits, you have to have tensor product. So I guess with quantum circuits, when you have 2 R's side by side, you're already having tensor product, but that's you can't really calculate with quantum circuits. And so instead of doing matrices and vectors and bracket notations, in a different approach, which I assume maybe you guys are familiar with as you're here, is to use quantum graphical calculi, where you use a different formalism that's graph-based for the calculation. So here are 2 rules from the ZX calculus, and these are all we'll need to do the example of quantum teleportation. And so this left side of this slide is the identity rule. It says that if you have 1 input, 1 output, red spider or green spider, they're called spiders because they get multiple legs, then if you rotate about the x-axis 0 degrees, it's the identity. And if you rotate about the z-axis of the block sphere 0 degrees, it's also the identity. We also have the 2 fusion rules, which I probably don't need to explain it, but to this audience, but if you're collected 2 colors at the same spot, 2 spiders of the same color, and you're connected by at least 1 leg, then you can fuse them together and add their faces respectively, their angles respectively. So you can teach quantum teleportation with this way. Here's the same circuit of quantum teleportation from 2 slides ago, but now translating each individual state preparation, gate, and measurement into the ZX calculus. So we can still denote the measurements, except now the measurements are just labeled by 2 total bits. There's 4 possible measurement outcomes in this spell basis measurement. And applying the rules, you can fuse and yank an identity and fuse. So I won't spend as much time into this to save more time for questions, but But this is a proof that having these top two qubits belong to Alice and the last qubit belongs to Bob. Then by rewriting, showing that each of these diagrams is equal to the same matrix, well, four matrices because it's the four possible bits, then all of these, no matter these four possible bits, you always end up for the straight wire from Alice going to Bob. So this is a proof that the input state, whichever it is that Alice had, is always teleported to Bob. So to get into the experiments, the main objective was to look at the zone proximal development. This means this is a zone that's in between what students can do independently on their own versus can do without guidance. Like you cannot do even with guidance. So here in the middle, it's what the students could learn if they were guided or taught. And we gave them a exam at the end of the course that was taught. And then at the end of the course, we gave them this exam. It had questions from past University of Oxford graduate course that has been running for over a decade in the computer science department. And the training was a flipped classroom approach. So this is 8 pre-recorded lectures. So they had more time, flexible time to learn the material. And then the time that they did have with the instructors was live tutorials or hands-on examples. 1 hour each, maximum around 15 students per tutorial. This was all an online course, so we could get some geographic diversity across the UK. The textbook was this textbook, the Quantum and Pictures textbook. This back cover is not up to date, but the front cover is here by Bob Kuka and Stefano Goggiosa, printed out last year. And the textbook shows these diagrams in space and time. So the kind of key kind of thinking in the very first lecture is just to think abstractly for the students to think about boxes and wires and processes. So for example, flowcharts, logic diagrams, circuit diagrams are the examples where you've got one of the, like say, horizontal or vertical axis being space and the other being time. So here's a list of the concepts that are taught in the 8 weeks lectures. And I should mention, we also don't have them required to know complex numbers or trigonometry, which would be needed if you used with a matrix vector approach. We can avoid the complex numbers because we can still express all matrices with all kinds of complex numbers, but the students just need to know about these real valued angles, these phases, which are between 0 and 2 pi. So here's a screenshot that says a 10-year-old also enjoyed it. Selection process was 734 applications within the 3 weeks. So, but then we had to also make sure there was a gender balance. It says time commitment here. We actually didn't select based off time commitment. We just took it into account, but we didn't select based off of it. And I don't think we didn't give them an English exam either. So in the end, we had 54 people complete the course in the end. The main thing we did assign this, like pick the students for, was to make sure there was a spread of students across different types of schools. So a majority of the students are from state schools to show that we're more representative of the UK population rather than say all from the same private school or something. So the learning materials, like just some screenshots of the lecture videos, looks like this. The quiz screenshots from the quizzes looks like this. And to see the test scores, so here's the ZPD diagram again. And the test scores, they were marked double blind by the University of Oxford rubric and methodology. So 2 people marking, and if there's discrepancy of more than 10 points, a third person marks, and all 3 people are employed. So by or teaching people at University of Oxford faculty. So this bold here is the numbers with a canary question. So this is a question that had a definition question from the last 1/3 of the course. And so if you include that filter, then more than 4 and 5 students passed, and around 1 and 2, more than 1 and 2 had a distinction, which is the highest grade category in the UK. So it's between 70% and 100. If you don't include that question, you still have a very good performance. Just for curiosity, then over 35% has a distinction, which is still more the highest grade category, which is still exceeds the fail percent. And this distinction question, this canary question was just a filtering. This filtering question was just a spider vision. So here's the exam distribution, exam score distribution. So you can see that all scripts without this definition question gets a kind of trimodal distribution, but the bottom one, most one, is these people did not get even the definition of a spider fusion. So maybe they didn't watch the lectures because we didn't incentivize them to do anything to do well on the exam at all. We said if they turn in anything, any exam, even if it's like blank, they'll still get, well, not if it's blank, but if they turn in anything, they'll still get the certificate of completion if they had a good enough attendance. So that way it takes the stress off of them. So the exam scores correlates poorly with the maximum study hours per week, as well as their school grades in math and physics. It just means that you didn't have to do well in your math and physics courses in high school in order to do well in this kind of graph-based manipulation and conceptual understanding. So the second question of the exam is conceptual understanding of a multi-step quantum communication protocol. We can't release the questions because we have I plan to do this, use the same questions for other countries' experiments of the same sort, so that it can be a baseline to compare with respect to different countries. But we can say a bit about what the questions were about. So this is interesting because I guess for the first time you can teach the maths without needing the exact presentation of the maths as matrices and vectors. So the hope is that this can be a more beginner-friendly presentation where you're still rigorously teaching the same maths, but you're not having like late undergraduate level of mathematical prerequisites. And here's just a slide to show that most of the students, because this was during their exam preparation, and these are high school students aged 16 to 18, all of them had exam preparation commitments because there's these annual exams. More than 1 in 5 had a part-time job, so some students would email saying, I can't make it to my classes, it conflicts with my job, and called into work. More than 1 in 10 had an internship, and many of them it was their leisure time.
Lia, we're gonna switch in 1 minute.
Okay, so yeah, this is the screenshot of hours per week that they spent on the course. Just asking them how much time. So it looks like it wasn't too much time they had to spend. Almost all of them spent less than 4. I think this means everyone spent less than 4 hours a week for the 8 weeks. And the course, here's just, maybe I'll stop on this slide because I think it's the end. But the course motivated more than 9 in 10 out of the students agreed that this course motivated them to pursue a STEM career. And that's a really high number because maybe these students weren't planning to pursue a STEM career in the first place. More than 7 in 10 agreed that it strengthened their motivation and confidence.
Okay. Lia, I think with that note,
okay.
Yeah,
and I'll also stop at this slide. You can read it, but it's just like a list of countries.
Right. Thank you very much.